Did you know that the Big Bang didn't just happen once, but is effectively still happening at the farthest reaches of your observable universe? That's right! All those early universe stages like inflation, the Quark-Hadron transition, and recombination still play out at the very edge of what you can see. In today's video, we'll explore the first 380,000 years of cosmic history and uncover how all these steps shaped and continue to shape our reality. Before we dive into the wild ride that is the Big Bang, let's talk about why this even matters in the first place. As we discussed in our observable universe and sunset conjecture videos, everything we see is in the past. Why? Because light takes time to travel from point A to point B, even at 186,000 miles per second. In reality, the farther out you look, the deeper in time you're actually seeing. That's why NASA's James Webb telescope is able to peer back to when the universe was only 400 million years old. So, if everything we see is in the past, then what's the farthest that we can see? Well, the answer to that is the beginning of time, or the hypothetical Big Bang, ultimate cosmic sunrise, or singularity sunset that's unique to you. Now, although the greater universe with a capital U, which refers to everything that exists whether we can see it or not, has no clear center, your idea space, or your mind, sits at the center of your own observable universe, a giant sphere centered on you where everything you see is in the past. And at the edge of this observable universe, on the outskirts of what you can see right now, lies the ancient epochs of the Big Bang we'll dive into this video. With that framing, let's venture into each layer of the Big Bang era, filling out this graphic and detailing what happened, the time of the event, and the temperature of the universe at that time in Kelvin. To convert Celsius to Kelvin, simply add 273. For instance, 23 degrees Celsius is 296 degrees Kelvin. The early universe was really freaking hot. For a reference, the center of the sun is around 10 to the 6th Kelvin, while the early universe was around 10 to the 32nd Kelvin. Hot mama, that's hot! Also, keep in mind that ever since the universe's inception, it has been continuously expanding and cooling due to dark energy. Even now, dark energy is continuously stretching the fabric of space around us. Furthermore, the universe was opaque for the first 380,000 years, as it was too hot and dense for light to move around freely. Lastly, if you want more details on any of this, then feel free to check out the bonus chapters linked below. Okay, we start at time zero, or at least as close as we can get to it with physics. The Big Bang. What came before the Big Bang singularity? No one knows. That remains a mystery. Renowned physicist Stephen Hawking once said, "The singularity is outside the scope of presently known laws." Was it a universe that went from nothing to something? Or a sort of rebound from one universe to the next? No one really knows. For the sake of discussion, let's assume the universe went from nothing to something, exploding everywhere all at once. During this time, we can represent our observable universe as a topological singularity, a sphere of zero measure and uncountable depth. Next up, Planck Time, which is around 10 to the negative 44 seconds after the Big Bang, where temperature soared to 10 to the 32nd Kelvin, scorching hot by any standards. A good way to think about Planck Time is to the universe as the seconds are to humans. Up to this point, all fundamental forces, gravity, electromagnetism, the weak force, and the strong force were hypothetically unified. Then came symmetry breaking, and gravity split off from the rest of the forces in the next time period we'll talk about next. Furthermore, the patch of space that would later become our observable universe during Planck Time might have been around 35 micrometers wide. This is according to physicists Edward Kolb and Michael Turner, and this 35 micrometers is half the size of a human hair, which is insane because today our observable universe is closer to 96 billion light years wide. That's crazy, right? Next is Grand Unification Epoch, which starts a little bit after Planck Time up until around 10 to the negative 36 seconds. In Grand Unification, the three forces, electromagnetic, weak, and strong, likely remained merged into a single unified superforce. In other words, the particles associated with each of the three forces, photons, Z and W, bosons, and gluons, were merged into one. Gravity has no particle assigned to it because quantum theory does not have a sustainable method for describing it. This is where the conundrum of quantum gravity comes in. Essentially, Quantum gravity is like asking, what is the fabric of space-time? Furthermore, during this epoch, particles from the standard model like quarks and leptons, which are called fermions and combine to make all of the atoms and matter as we know it, were also unified, one and the same, completely indistinguishable. Then, as the universe expanded and cooled, forces and particles began to differentiate from one another. Hawking likened this symmetry breaking to a roulette wheel. When the wheel spins quickly, analogous to a high energy state or a hot temperature of the universe, the ball rolls around in a single state, similar to the unified forces and particles. But as the ball slows down, mirroring the universe's cooling, the balls drop into one of the many different slots, revealing the distinct types of forces and particles we see today. Then comes inflation. When the universe expanded by a factor of about 10 to the 26 in length. That's one with 26 different zeros. Imagine yanking a crumpled picnic blanket so fast that it just flattens out. That's our universe inflated into near flatness outside of global galactic clusters that were created later in the universe's life. This huge inflation marks a period of supercooling, but as soon as inflation ended, the universe reheated to phenomenal temperatures reminiscent of pre-inflation in a flash. With all these crazy changes, it's no surprise that the strong force split from the other forces at this time. After inflation, the universe is still hot, so re-enter the hot Big Bang. When a searing quark-gluon plasma basically dominated the universe, matter and antimatter pairs popped in and out of existence, annihilating one another into a local thermal equilibrium. An antiparticle contains the same exact properties as the original particle, except it has the opposite charge. For instance, if an electron has a charge of -1, then an anti-electron or positron has a charge of +1. When a particle and its corresponding antiparticle come into contact, they completely annihilate one another, converting all of their mass into pure energy via Einstein's famous equation E=mc². As the universe cooled from this primordial soup, it soon entered an energy range we can partly replicate in modern laboratories, thereby setting the stage for the next big milestone, the split of the electromagnetic and the weak force. Here, the electromagnetic force, light or photons, and the weak force, W and Z bosons, finally go their separate ways, and all four forces are independent. During this time, the Higgs mechanism also kicks in, giving mass to most of the fermions and some of the bosons. Before this, nearly everything was radiation, particles zipping around at or near the speed of light. Now, particles can finally slow down enough to become matter as we know it. Next, the universe kept cooling and expanding enough for the Quark-Hadron transition, when quarks were able to bind into larger particles called hadrons, like protons and neutrons. For instance, a proton consists of 2 up quarks and 1 down quark connected by gluons, while a neutron consists of 2 down quarks and 1 up quarks also connected by gluons. Quarks are a weird and wacky world that deserve their own video, so make sure to subscribe to stay in the loop. Even though this step marks the dawn of stable atomic matter, it's still way too hot for electrons to attach to nuclei and for photons or light to travel around freely without just colliding into something. The universe is still opaque, a swirling soup of particles. We finally move beyond microseconds into the Lepton Epoch. After most of the hadrons and anti-hadron pairs annihilated one another, leptons, like electrons, became more influential by sheer survival of the fittest. A tiny imbalance called baryogenesis ensured that there was just a smidge more matter than antimatter, leaving matter to eventually triumph overall, which is why we have things today. For instance, before 10 to the -6 seconds, there seemed to be around 30 million and 1 quarks for every 30 million antiquarks. Also during this time period, neutrinos decoupled from the thermal equilibrium and traveled freely to form the neutrino cosmic background. Imagine a pinball machine where neutrinos are able to fly, but nothing else. Let there be light! We're now officially in the Photon Epoch. From here, electron-anti-electron pairs commence their annihilation process, similarly to the quarks and antiquarks from the last epoch we looked at. This let light dominate. Since everything we see is in the past, you can really think of light as a cosmic ghost of Christmas past, spanning countless different wavelengths, from radio waves that are as tall as buildings to gamma rays the size of atoms. Yet, the early universe was still too packed tightly for light to travel freely. Photons constantly collided with electrons, quarks, and other photons, leaving the cosmos completely opaque. Hooray! Hooray for what? We finally have atoms with nucleosynthesis. The universe is finally cool enough for nuclei to form. Hydrogen, helium, and tiny traces of lithium emerge. These are the simplest atomic nuclei with 1, 2, and 3 protons respectively, which makes sense for why they formed first. Stars, supernova, and cosmic radiation will later forge some of the heavier elements. Believe it or not, everything up to now transitions within just a few minutes. More change in the first 3 minutes of the universe than the remaining 13.8 billion year lifespan of the universe. We now jump to 50,000 years when the universe went from radiation dominated to matter dominated. This means that more slow-moving particles exist than those that move at near or at the speed of light. This lays the foundation for structural formation of stars, galaxies, and eventually us. Due to this change, we have a fascinating situation where the universe's expansion is decelerating, not accelerating. Now, the universe is still getting bigger, just not as fast. Think of it like a car easing off the gas pedal. It's still going forward, just slower. This cosmic slowdown continues for billions of years until, plot twist, dark energy takes over and completely flips the script once again as the universe starts accelerating. Finally, at around 380,000 years, the universe is cooled enough for electrons to bond with nuclei, creating neutral atoms in a process called recombination. Now, this name is a complete misnomer, as electrons and nuclei were never really combined, but what's in the name anyway? With fewer free electrons around, photons decoupled from the rest of its surroundings and could finally travel freely, making the cosmos completely transparent and marking the era of the cosmic microwave background, or the CMB. This CMB is the earliest photo of our universe when it was 380,000 years young. During this time, the composition of the universe was around 63% dark matter, 15% photons, 12% atoms, and 10% neutrinos, which is quite different than what we see today, which is 68% dark energy, 27% dark matter, and 5% atoms that we have come to know and love. After this phase, we start getting our first stars, black holes, and galaxies, which are topics of our upcoming videos. And there you have it, a whirlwind tour of the first 380,000 years of cosmic history. From a mysterious singularity at around 10 to the 32nd Kelvin to a transparent universe full of atoms at 3000 Kelvin, each stage is etched into the sky at the very edge of our observable universe today. Why? Because everything we see is in the past, as it takes time for light to travel from point A to point B, even at 186,000 miles per second. The Big Bang is still happening at the farthest reaches of your personal singularity sunset. And if the universe is constantly birthing itself anew, then why shouldn't you? If you enjoyed this deep dive into the Big Bang era, like this video, subscribe, and ring that notification bell so you won't miss out some of our latest videos. In the next video, we'll take a look at the complete life cycle of stars, from their inception to their death and life after death. So make sure to stay tuned. Thank you for tuning in, and I shall see you next time. Adios, peace, ciao, ciao, bye. Whoa, 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 whoa. All right, those are my favorite part of the videos, just so you know.